When discussing virtualization, there are several types or modes that define how the hypervisor interacts with guest operating systems, OS, and their resources. These modes impact performance, isolation, and compatibility with guest operating systems. The three common categories are full virtualization, partial virtualization, and containerization or OS-level virtualization. Let's break down each mode. Full virtualization is a method of virtualization in which the guest operating system runs without knowing it's being virtualized. The hypervisor provides a complete virtualized environment to the guest OS, which behaves as though it's running on a physical machine. Key characteristics include that the guest OS is completely isolated from the host and other VMs. The hypervisor fully emulates all hardware components, CPU, memory, I/O, network devices, etc. To the guest OS, no modifications are required to the guest OS for it to run in a virtualized environment. And full virtualization can be hardware assisted by CPU features like Intel VTX or AMD V. Examples of full virtualization hypervisors include Hyper-V, when using hardware-assisted virtualization, VMware, vSphere, ESXi, KVM, kernel-based virtual machine, with hardware support, and Zen with hardware-assisted support. Use cases for full virtualization include running unmodified guest OSes, Windows, Linux, etc., in isolated environments, running legacy applications or operating systems that require complete hardware isolation, and it is ideal for server consolidation, as it allows multiple OSes to run on the same physical hardware without requiring them to be aware of each other. Advantages of full virtualization include isolation, as each VM is fully isolated, so problems in one guest OS don't affect others, and compatibility, as full virtualization supports a wide range of guest operating systems, including those that are not designed to run in virtual environments. Disadvantages include performance overhead, as the hypervisor emulates all hardware. There is a performance penalty compared to running on physical hardware, and it is resource intensive, as emulating hardware and running multiple VMs can consume significant system resources. Partial virtualization is a method where the guest operating system is aware it's running in a virtualized environment. The hypervisor does not completely emulate all hardware components. Instead, it partially virtualizes them, allowing the guest OS to directly interact with some of the underlying hardware, while the hypervisor manages others. Key characteristics include that some part of the guest OS may be modified to work in a virtualized environment. The guest OS may need special drivers or support to run efficiently in the virtual environment. Not all hardware is virtualized, and it is typically used in scenarios where the guest OS can handle some operations itself, and the hypervisor only manages critical components. Examples of partial virtualization hypervisors include Zen in some configurations, VMware Workstation, and VMware Fusion, when not using hardware-assisted virtualization, and OpenVZ for containerized virtualization, though it's closer to containerization. Use cases for partial virtualization include performance-sensitive applications where virtualization of only certain resources, CPU, memory, is necessary, and environments where guest OS supports some level of virtualization, e.g., older operating systems or proprietary OSs. Advantages include lower overhead, as the hypervisor does not need to fully emulate hardware, and better resource utilization, as the guest OS may be able to access some resources directly, reducing the strain on the hypervisor. Disadvantages include limited OS support, as the guest OS may need to be customized or aware of the virtualization environment, and complex configuration, as it may be harder to configure compared to full virtualization, especially for less experienced administrators. Containerization is a form of operating system level virtualization, where the hypervisor doesn't provide full hardware virtualization. Instead, it provides a shared kernel environment for multiple isolated containers. Each container runs as an isolated process in the user space, but all containers share the same underlying OS kernel. Key characteristics include a shared OS kernel, as all containers share the same OS kernel, but are isolated from one another, being lightweight, as containers are generally more lightweight than virtual machines because they don't require a full OS per instance, fast boot times, as containers can start and stop very quickly, and isolation, as containers are isolated from one another. but they run on the same OS and kernel. Examples of containerization platforms include Docker, Kubernetes for managing containerized applications, and LXC, Linux containers,